SwayamPrabha. Digital India. Educated India.
I welcome you all to the session of thermal engineering basic and applied, and today we shall discuss about the flow nozzles. You know that in the context of steam power plant, which is one module that a module of this course that we have discussed, flow nozzles are also very important, rather these are mandatory components. Though if we try to recall in the schematic depiction of the steam power plant, we did not mention about the flow nozzle, but we had mentioned about 4 major components like steam generator, steam turbine, condenser and pump. So, if we try to draw the schematic of a steam power plant, and we can see the major components So, you know this is the schematic depiction we have used many times. What we can see, we started our discussion with the steam power cycle. Though we have briefly discussed about the basic thermodynamics which are important to understand the processes, rather all the processes which are there in the steam power cycle. We have also discussed about the steam power cycles. Several cycles we have discussed, starting from the Carnot cycle, Rankine cycle, modifications of the Rankine cycle, and we have also discussed about binary cycle. Then we have discussed about the steam generator or boilers. Now, before going to discuss about steam turbine, today we shall discuss about the flow nozzles. We cannot see the nozzle in this schematic depiction, but again nozzles are the mandatory components in the context of the operation of the steam power cycle. Try to recall, steam generator, the sole purpose is to produce steam, and that steam when it is coming from the boiler is having high temperature and pressure. That high temperature and pressure, that having high energy, to be precise, that energy should be converted into the another form of energy, that is work. So, that work we will be getting. Now, how can we have this conversion? So, at the exit of the boiler, steam which is being produced, that steam is having high temperature and pressure. From that high temperature and pressure of steam, if we look at the exit of the turbine, we are getting again steam, but that steam is having low temperature. So, turbine is a device in which high pressure, high temperature steam is doing some work and that steam is leaving the turbine which is having low temperature. So, and that temperature is almost the condenser pressure. So, basically temperature has dropped, pressure has reduced, and at the cost of this reduction in pressure and temperature, we are getting some work output. So, that energy conversion takes place in the in the turbine. Now, when we are talking about energy conversion, that energy conversion takes place in two ways. So, at least we have understood that steam turbine I am sure that you all have studied about hydraulic turbines. What is done? Where these hydraulic turbines are used? Because we have studied that hydraulic turbines are used to generate electricity in a hydraulic power plant or hydel power plant, and we have seen that we use the energy which is remaining stored in the water, and water is allowed to flow through a penstock, and finally depending on the types of the turbines, whether it is, if it is an impulse turbine, then water is taken through the nozzle before it enters the impulse turbine blades. So, basically stored energy of the fluid that is converted into the kinetic energy. So, here also when you are talking about steam turbine, the energy which is remaining stored, internal energy plus that high pressure and that temperature, that is now converted into another form of energy in the turbine, and that conversion takes place following two ways. So, in the steam turbine, this energy conversion takes place. There are two ways. First, high pressure and high temperature steam is allowed to flow through the nozzle. Right. So, first steam is allowed to flow through a nozzle. Nozzle is again a mechanical device which is having gradually decreasing area. If a device which is having gradually decreasing area in the direction of flow, that is nozzle, if it is having gradually increasing area in the direction of flow, that is diffuser, sometimes a device may have decreasing and then increasing area. So, that is convergent divergent nozzle. So, the nozzle is having convergent shape, that is the area of that device decreases in the direction of flow. So, when that high pressure and high temperature steam is allowed to flow through the nozzle, at the reduction of that high pressure, velocity increases. So, flow velocity increases, right. So, what we can see that initially steam will be allowed to pass through the flow nozzle, and while passing through the nozzle at the reduction of the pressure drop, I mean at the cost of the pressure drop, flow velocity will increase. Second is high velocity steam jet. It is designed, nozzles are designed in such a way that while steam is passing through the nozzle, there should not be any drop of temperature. So, temperature should not be allowed to reduce while steam is passing through the nozzle. So, there is no chance of having reduction in steam temperature theoretically. Now, so that means we are also going to get steam at the exit of the nozzle, and since the velocity of the steam will be increased, now we are writing steam jet. So, steam will come out of the nozzle in the form of a jet. So, high velocity steam jet is now allowed to impinge the turbine blades which are mounted on the wheel of the turbine what would be the consequence? So, when steam jet, rather steam is coming out of the nozzle in the form of a jet, that jet impinges turbine blades which are mounted on the wheel of the turbine. Now, you have studied blades when you have studied about hydraulic turbines as well as pumps. So, blades are twisted. So, blades are not, blades are having some shape and blades are twisted. So, when steam jet impinges turbine blades, and then there will be a change in the direction of steam. So, consequence is that after impingement, steam direction will be changed. So long as the change in direction then there will be a loss of momentum. So, when steam jet is coming, steam is coming out of the nozzle in the form of a jet, that jet impinges turbine blades and that jet will have deflection because of the inherent structure of the turbine blades. Now, when there is a change in direction of the steam jet, the jet will suffer a loss of momentum. So, I am writing steam jet will have a change in direction while passing through turbine blades. Then then there will be, or the steam jet will suffer from a loss in momentum. So, that means you know that the momentum of steam jet will be lost while passing through the turbine blades. So, I mean you know that nothing is lost, that loss in momentum will be absorbed by the rotor or wheel. So, that loss in momentum will be absorbed by the turbine wheel and that will produce torque. So, this momentum will be absorbed by the turbine wheel and the ultimate consequence is it will produce torque. So, which is producing torque? Torque will be produced by the steam jet because of some mechanical arrangement, that means steam is allowed to have deflection in its flow path, and while there will be a deflection in the steam flow, that will, and it is because of this reason steam jet will suffer a loss in momentum, and that momentum will be absorbed by the turbine wheel, which in turn will produce torque, and it is because of that turbine wheel will be rotated. So, this is how you know the energy conversion takes place inside the turbine. So, today just I wanted to discuss about how this high pressure high temperature steam is you know going through. When the high pressure high temperature steam is passing through the turbine, we are getting or we are having energy conversion. Eventually, you are getting steam at the exit of the turbine, but the steam is having low temperature. So, now what we can see that it is not only the turbine itself, rather inside the turbine we also need to have a few flow nozzles, and this is why I have taken this particular aspect today at the beginning, in the beginning, so that we can have fair understanding about the utility of flow nozzles in the context of the steam power plant. So, when steam is allowed, steam is coming out from the boiler or steam generator, that steam is not directly taken to the turbine blade, rather steam is allowed to pass through the flow nozzles, and then only that high velocity steam jet will be taken to the turbine blades, and we have seen by how we are getting energy conversion which is taking place inside the turbine. So, what we can see that steam turbine is the assemblage of the flow nozzles and turbine blades. So, let me write here steam turbine is the assemblage, steam turbine is the assemblage of flow nozzles and turbine blades. So, these two mechanical parts together is the steam turbine. Today we shall briefly discuss about the flow nozzle. So, why flow nozzle is very important we have understood. Flow nozzle. So, that means it is a mechanical device, it is a nozzle through which steam is flowing. So, when steam is flowing, that we need to have the analysis of that flow essentially to see, because the entire objective of the flow nozzles is to produce steam jet. So, if we draw the shape of the flow nozzle, so this is the flow nozzle, so this is the flow direction, right. In the direction of flow there is a decrease in the cross sectional area. So, when the area is reducing, mass flow rate will remain same. So, velocity will increase. Since the fluid here is the steam, so it is very difficult to say that the density will remain constant. So, density will also be varying when steam is flowing from one part of the nozzle to the another part of the nozzle. So, we also need to understand that for a given mass flow rate of steam, because that mass flow rate will be produced by the steam generator, if we take a particular nozzle, then what would be the nozzle area at the exit, at its exit, so that we can get required velocity, which is very important, because the steam jet which will be produced at the exit of the nozzle, that steam jet will be now directed to the flow, I mean it will be directed to flow through these turbine blades. While it is passing through the turbine blades, first it will impinge. So, the impingement, the rate at which it will impinge on the turbine blades, that depends on the velocity of steam at the exit of the nozzle. So, you can understand the area at the exit of the nozzle also an important parameter to be looked at for the proper or efficient operation of the energy efficient energy conversion that will takes place in the turbine. So, these are the flow nozzles. So, this is convergent type. So, this is convergent type. So, this is 2, this is 2, this is 1, this is 1. So, 1 that is inlet, 2 that is outlet. There are 2 sections. Now, we may have similarly that divergent type. So, we may have divergent type. So, this is the flow direction. This is called just which is opposite to the flow configuration that we have seen in this particular case. So, this is divergent, and normally that we understand nozzle is basically having gradually decreasing area in the direction of flow. So, this is basically this is the typical shape of a nozzle. So, but this is also we can say diffuser, because in the direction of flow area increases, and we may have another one type, that is so this is 2 2, this is 1 1. So, this is the flow direction. So, this is neither purely convergent type nor purely diffuse divergent type. So, this is called convergent divergent type. So, this is basically I am not writing diffusion now. So, this is divergent type. So, this is divergent type. and this is convergent divergent type. So, these are the different types. So, now let us consider the flow through a nozzle. So, we shall be considering the flow through a nozzle. I hope you have understood that the basic objective of studying the flow through nozzle is to know the velocity which the steam will have at the exit, because that is important parameter, and to get that velocity what would be the area at the exit of the nozzle. So, flow through a nozzle, we take a few assumptions. What are those? We consider that flow through the nozzle is isentropic. So, you have studied it, flow through the nozzle is isentropic, that means there is no heat transfer. When steam is flowing through the nozzle, there will not be heat transfer from the steam to the surroundings through the nozzle wall. So, basically if we consider, if that is the nozzle, we assume that this is convergent divergent type, this is 2 2, this is 1 1. So, this is the convergent divergent type nozzle, and we can see walls of the nozzle are insulated. So, there is no heat transfer, and also the frictional effect is negligibly small. So, first of all there is no heat transfer, isentropic. So, no heat transfer, from the steam to the surroundings, right. Number 2 is frictional effect is I can say no negligibly small. While you are talking about frictional effect, internal friction plus external friction. Internal friction is friction between the fluid layers. So, when steam is flowing through the flow nozzle, friction between the fluid molecules or frictional of the fluid molecules between two adjacent layers. So, when there is friction between the two adjacent layers is neglected, together with the friction of fluid and the solid wall is also neglected, that is external friction. So, here both internal and external friction. Internal friction is the frictional effect between two adjacent fluid layers, and external friction is the friction between fluid layer and the solid wall. So, these two effects, two frictional effects are neglected. So, this is number 1. Number 2 is an isentropic process. So, that is very important. Now, isentropic process, so basically flow through the nozzle is isentropic, and we have assumed that there is no friction. Isentropic process steam is, we are assuming that the flow is compressible. So, flow of steam so we are assuming that is compressible fluid. Okay. So, we are assuming that is P equal to constant, that we have studied. I am not going to discuss on this part. So, we can write P by 1 upon rho to the power k equal to constant. So, the specific volume I am writing in terms of density. So, this is the mathematical expression of the isentropic process. So, we are assuming, we are modeling the flow like this equation using this equation. So, we have assumed that the flow is isentropic. For the isentropic process, we are mathematically modeling using this equation, that is P by rho to the power k is equal to constant, and this k is the index of expansion of the isentropic process. So, here let me write here, k is index of expansion of the isentropic process. Okay. So, this is number 2, we can write this flow is one dimensional, right. So, we assume the flow is 1D, and number 3 is steady state analysis, steady state flow analysis. So, basically these are the assumptions we have taken. So, these are the assumptions. So, these are the assumptions we are considering: isentropic flow, no heat transfer, 1D flow, and we are going to have steady state flow analysis. And for the isentropic process, we have mathematically modeled the system using this equation, mathematically model the flow scenario using this equation, that is P upon rho to the power k is equal to constant, and k is basically index of expansion of the isentropic process. It depends on the, so k equal to Cp by Cv. Okay. So, that we are going to have. Now, if we stick to this particular geometry, then how can we write the equations? Okay. So, pertaining to this configuration, if we assume that normal to the flow direction, area of cross section is A, at the we are going to have say certain cross section. So, if we consider certain section of the duct, any section, say if we take this is the cross section, right. So, considering certain cross section in the duct, and if we assume that area of the cross section is A, which is normal to the flow direction. So, we have assumed that is the cross section, right. Say this is the cross section 1 prime 1 prime, and area of that cross section is A, which is normal to the flow direction. Okay. So, normal to the direction of fluid flow, that is the surface area. So, this is A, surface area normal to the flow direction. If we assume that rho is the density of the fluid, so at that particular section assume rho is the density, c is the fluid velocity, h is the specific enthalpy, okay. So, this is C is the fluid velocity, h is the specific enthalpy, rho is the density and v is the specific volume, small v is the specific volume of the fluid at that particular section, and z is the elevation, z is the elevation of that section from the datum, okay. And P is the pressure, right, Z is the elevation of the duct, P is the pressure, okay. So, we have assumed one particular cross section in the duct, we are considering A is the cross sectional area of that particular surface which is normal to the flow direction. We have also assumed the fluid properties like rho, that is density, specific enthalpy, specific volume, pressure. We have also assumed C is the fluid velocity and we are assuming Z is the elevation of the duct, okay. So, if we write this, then what we can write? We can write, so from continuity equation, what we can write? We can write from the continuity equation is, we have assumed that at any particular cross section those are the fluid properties that we have listed down over here. So, that means from this continuity equation we can write rho 1 A 1 C 1 equal to rho 2 A 2 C 2 equal to rho into A into C equal to constant, because mass flow rate of steam is constant. So, if we taking log both sides and if we differentiate it, what we can write is, so if I come to the particular slide, so rho A C equal to constant. So, if we do these steps, we will be getting dA upon A plus d rho upon rho plus dC upon C equal to 0. So, this is equation 1. We are considering, so this is what we have obtained from the mass conservation equation, and if we take log both sides and we differentiate it, we will be getting this. So, this is equation 1. See, before, I mean few minutes back I have discussed that the objective of the flow analysis through the nozzle is to know what would be the area at the exit of the nozzle to get the desired flow velocity of the steam, and that velocity is essential because higher the velocity of the steam jet, higher will be the impingement, deflection will be more, and because the momentum that will be absorbed by the turbine wheel, that will depend not only on the steam velocity at which that steam is impinging the blades, also the blade angle, but it will largely depend on the velocity of steam that we are going to get at the exit of the nozzle. So, but there are several other issues that we shall discuss. Now, question is, if we look at this particular equation, we can understand that somehow we could relate area with the velocity of steam along with the steam property, that is density. We have discussed that it is, we are considering steam as the compressible liquid, compressible fluid. So, density of steam is not remaining constant throughout the nozzle. So, density will vary. So, we have also taken that particular effect into account while arriving at this equation. So, this is fine. So, our objective is to get velocity with area. So, what would be the area of the nozzle at the exit of the, what would be the area of nozzle at its exit? Knowing the area at its inlet, we can calculate velocity. So, we have to relate this d rho by rho in terms of other known quantities, because the density will have continuous variation in the flow path. So, we know the area of the nozzle at the inlet, we can design the area of the nozzle at the outlet, and that is very vital parameter essentially to have the variation of the flow velocity. So, the density will change. So, now we have to relate this change in density with some other known parameters, so that we can close this equation. Very nice. So, what we have seen? We have seen that P by rho to the power k equal to constant, that is from the isentropic process. Okay. So, if we differentiate it, we can write what we can write, 1 upon rho to the power k dp minus k p by rho to the power k plus 1 equal to 0. So, we can write dp by p equal to into d rho equal to, we can write dp by p equal to d rho by rho, right, 1 by k d rho by rho, 1 by k dp by p equal to d rho by rho. So, that is another important equation. As I told you that our objective should be to relate d rho by rho with some other known quantity. So, this is equation number 2, right. So, if we plug in the value of d rho by rho in terms of dp by p in this equation, we will be getting the new equation. Now, we have also assumed that the analysis is steady state analysis. So, if we recall the steady state steady flow energy equation, then what we can write? So, if we consider the steady state steady flow process, then the steady flow energy equation SFE. So, this is a process, and while this process is getting executed, there is no heat and work interaction. Let us look at this particular schematic. What we can see? Steam is flowing through the nozzle, but while the steam is flowing through the nozzle, the process will be completed, but to complete this process we do not have heat and work interaction, because we are keeping the walls of the nozzle are insulated. So, there is no heat loss. Now, if we write this equation, we will be getting H1 plus C1 square by 2 plus Z1 equal to H2 plus C2 square by 2 plus Z2, right, that we can write. I can write 2G because I did one mistake. So, this is the equation, right. So, H1 plus C1 square by 2 plus GZ1, sorry, here I can write like this, plus GZ1 plus GZ2, sorry. Now, what we can So, this is the equation. So, from there, because in absence of heat and work interaction. So, I am writing over here steady flow energy equation in absence of work and heat interaction. Work and heat interactions. Mind it, while writing this equation, we have considered the work which is needed to maintain the flow in the presence of pressure, that is we have taken into account. So, this is what I have, this aspect I have discussed when I have discussed about the basics of the thermodynamics, which will be required to understand the rather we shall be recalling those aspects frequently while discussing several aspects of different modules of this course. But while writing this equation, we have taken into account the work done which is needed to maintain the flow, because there will be continuous flow through this convergent divergent nozzle or the fluidic channel. So, to maintain the flow continuously, the work is needed, and that work, that expression is already taken into account in this equation. So, this is what we are writing in absence of work and heat interaction, that is work between system and surroundings and heat interaction between system and surroundings. So, if we trivially ignore the elevation change, so when the elevation change is neglected, because if the nozzle is not kept in a vertical configuration, or nozzles are tried to keep in a configuration which is having inclination angle very small. So, for that case we can trivially ignore the change in elevation. So, we can write H2 minus H1, that is we can write dH plus CdC equal to 0. So, H2 minus H1 or H1 minus H2, that is dH plus C2 square minus C1 square by 2. So, basically we can write that is CdC. If we integrate this equation, we will be getting this one. So, dH plus CdC equal to 0. So, that is the another equation, because we are trying to relate velocity with other properties. See, if we already mentioned the properties, that is density, fluid velocity, specific enthalpy, specific volume and the pressure. So, this is what we have written, because again you have to keep in mind that this is the flow of a compressible fluid through a duct having gradually increasing or gradually varying area. So, this is what we have written. Now, what we can next do is we can write the property relation. I mean, for any process we can write, for any process we can write this property relation TdS is equal to dH minus VdP, right, that we can write, and this is the property relation. So, we can write that is equal to dH minus dP by rho. Now, we have assumed that isentropic process. So, isentropic process, if we consider now isentropic process, that means ds equal to 0, there is no change in entropy. So, we can write from that dH equal to dP by rho. So, if we place this expression dH is equal to dP by rho in equation, this equation 3, then what we are getting? So, we are getting we are getting dP by rho plus CdC equal to 0, that is what we are getting, dP by rho plus CdC equal to 0. Now, what we can write it, that just to have some kind of manipulation, we can write dP by rho c square plus dC by c equal to 0. So, we are dividing by c square and then we can write this equation. Why you are doing so? So, now question is because we are talking about the flow through a duct which is having gradually varying area, initially decreasing then increasing, right. So, it is again the flow scenario of a compressible fluid. So, we know what is Mach number. So, Mach number is basically defined as the ratio of velocity of fluid at any particular section at any particular pressure and temperature, of course, velocity of fluid at any particular section at any particular temperature to the local sonic velocity at that section at that temperature. So, velocity Mach number is velocity of fluid at any particular section at any pressure and temperature to the local sonic velocity at that particular section at the same pressure and temperature. So, m equal to c by a, and you know what is a local sonic velocity, that is this a equal to under root k into, that is very trivial to understand because you all have studied it, k p by rho. So, that is k p by rho. So, you know that if we write basically, that means we can write m square equal to c square by a square, that is rho c square by k into p. So, this is p, k p by rho. So, what we can write from here is rho c square equal to m square into k into p, this is p. So, we can write dP by rho c square plus dC by c equal to 0, and we can place dP rho c square equal to kp into m square, kp into m square plus dC by c equal to 0. So, this is the equation that we are getting, right. If we just write it, we can write dC by c equal to minus 1 upon km square dP by p. So, this is again one term. So, if we go back to the equation 1, so see dC by c we got expression, and that is 1 upon km square into dP by p, right. So, what is d rho by rho? D rho by rho we also got 1 upon k dP by p. So, if we try to write all these equations and then we can relate the area of the flow nozzle in terms of the known quantities. So, what we can do? We can plug in the value of d rho by rho from equation 2 into equation 1. We also can plug in the value. So, this is 3, this is 4 and this is 5. So, if I write over here, so putting the expression of dC by c equal to minus 1 upon km square dP by p and d rho by rho equal to 1 upon k dP by p in equation 1. What we can write? We can write dA by A, So, this is the equation dA by A. What is d rho by rho? D rho by rho equal to 1 upon k dP by p, and then we are having dC by c. So, we can write it minus 1 upon k m square dP by p equal to 0. So, if we try to just write this term, we can write dA by A equal to dP by P into 1 upon Km square minus 1 upon K. So, that means finally we can write that dA by A equal to what we can write 1 upon K dP by P into 1 minus m square divided by m square, right. So, this is the relation we wanted to derive in today's class. This is very important relation. So, we can understand. So, this is equation number 6. So, this is the equation we wanted to derive in today's class, because we can see though we could write dC by C in terms of this quantity, dH d rho by rho using this quantity, finally we have written dA by A using the expression of dC by C and d rho by rho in this form, and the quantities which are there in the right hand side are known, because you know that we know the Mach number, and this K is also known because that is index of expansion of the isentropic process, and we also know what is the pressure drop that we are going to have. So, basically if we know the m, then probably we also know the velocity of fluid at any particular section as compared to the local sonic velocity at that section given the pressure and temperature same. So, basically using this relation we can find out what would be the area at the exit of the nozzle to obtain the velocity which is needed, knowing the drop in pressure and also the index of expansion of the isentropic process. So, the physical significance of this equation is tremendous, that we shall discuss considering several cases, and that part we shall do in the next class. So, with this I stop here today, and we shall continue our discussion in the next class. Thank you.